Have you ever felt like there's something more to reality than what we can see and touch? It's a natural feeling, but what if I told you that modern physics not only agrees, it takes that idea to a whole new level? We experience the world in 3 dimensions of space length, width, and height, plus 1 dimension of time, which relentlessly pushes us forward. Everything from the smallest atom to the largest galaxy cluster fits perfectly within this 4-dimensional box. It's our cosmic home, the stage on which the entire drama of the universe plays out. But for nearly a century, a profound mystery has been whispering from the equations of our best scientific theories. The universe, it seems, has a secret. When physicists try to unite the 2 great pillars of modern science, Einstein's theory of general relativity, which describes gravity in the large-scale universe, and quantum mechanics, which governs the bizarre world of subatomic particles, they hit a wall. The math breaks down. The theories clash. It's like trying to fit a square peg into a round hole. The only way the numbers seem to work is if we make a radical assumption that our 4-dimensional reality is not the whole picture. This is the birthplace of string theory and M-theory, ideas that suggest the fundamental building blocks of our universe aren't point-like particles, but unimaginably tiny, vibrating strings of energy. And for these strings to vibrate in all the ways needed to create the rich variety of particles we see, they need more room to move. They need extra dimensions. So where are they? Why can't we see them? Imagine a tightrope walker. From far away, the rope looks like a 1-dimensional line. You can only move forward or backward. But for an ant living on that rope, there's another dimension, the ability to walk around its circumference. The extra dimensions proposed by string theory could be just like that, curled up, codified, to a scale so infinitesimally small that we've never been able to detect them. They could be smaller than a single atom, folded into complex, beautiful shapes known as CalabiYau manifolds, hidden within every single point in our space. Another mind-bending idea is the brane world scenario. In this model, our entire 4-dimensional universe is just a membrane, or a brane, floating in a much larger, higher dimensional space called the bulk. We, and all the forces of nature except for one, are stuck to this brane. We are essentially shadows in a higher dimensional reality, unable to perceive the full expanse that surrounds us. This isn't just a mathematical fantasy. It offers a stunningly elegant solution to one of physics' oldest puzzles. Why is gravity so incredibly weak compared to other forces like electromagnetism? If you can pick up a paperclip with a tiny refrigerator magnet, that magnet's electromagnetic force is overpowering the gravitational pull of the entire Earth. In the brane world model, the answer is simple. Gravity isn't weak, it's just leaky. Unlike the other forces, gravity is not confined to our brain. It can seep out into the extra dimensions, diluting its strength. What we feel is just a faint echo of its true power. Scientists at the Large Hadron Collider are actively searching for evidence of these hidden dimensions. They smash particles together at nearly the speed of light, hoping to create tiny, fleeting black holes or to spot particles that suddenly vanish, possibly escaping into another dimension. Finding this evidence would be the single greatest discovery in the history of science, confirming that our reality is just a slice of a much grander, multidimensional cosmos. The existence of extra dimensions would rewrite our understanding of everything. It could explain the nature of dark matter and dark energy, the mysterious substances that make up 95% of our universe. It could even offer a glimpse into what came before the Big Bang, suggesting our universe was born from the collision of 2 branes in a higher dimensional space. We stand at a precipice, peering into an abyss of possibilities. The universe we know might be just one page in a vast multidimensional book. Unlocking these hidden dimensions isn't just about solving equations. It's about discovering the true nature of reality itself. Dynamic, stretching, warping, and constantly evolving entity. Our story starts about 13.8 billion years ago, at the moment we call the Big Bang. But here's the first big twist. The Big Bang wasn't an explosion asterisk in asterisk space. It was the birth of space itself. In the very first fractions of a second, the entire universe was incredibly small, unbelievably dense, and almost perfectly uniform. Then something extraordinary happened, an event called cosmic inflation. In a flash, space itself expanded exponentially, stretching out far, far faster than the speed of light. In less than a 10 millionth of a trillionth of a second, a region smaller than a single atom ballooned to a cosmic scale. This incredible burst didn't just stretch out matter and energy, it stretched the very fabric of dimensions. Physicists believe that it was during this violent inflationary period that the structure of space-time was set in stone, determining how many dimensions would unfold into the vast universe we see and which ones might remain hidden from view. Now you might be thinking, why just 3 dimensions? And that's a great question. Mathematically, there's absolutely no rule that says space must have only 3 dimensions. In fact, the equations of physics work perfectly well with many more. So, the real mystery is, why do we only experience 3? To find the answer, we have to go back to the geometry of that brand new universe. According to some of the most advanced models in physics, like string theory, when the universe first emerged from the quantum foam, might have had as many as 10 or even 11 dimensions. Picture a multidimensional fabric buzzing with vibrating strings of pure energy. As the universe expanded and cooled, a cosmic sorting process began. Some of those dimensions, our familiar length, width, and height, continued to expand, forming the vast 3-dimensional space we call home. But the others, they may have done something entirely different. They may have curled up on themselves, becoming so incredibly small, so compact, that they are now effectively invisible to us. Imagine for a moment that every single point in space, the tip of your finger, the air you're breathing, the space between, atoms contains hidden directions. Tiny loops folded in on themselves at an unimaginably small scale, perhaps a billionth of a trillionth of a centimeter across. If you could somehow shrink down smaller than an atom, smaller than a proton, smaller even than a quark, you might discover that space continues to twist and fold in on itself in ways our 3-dimensional minds couldn't even begin to visualize. These compactified dimensions aren't just science fiction. They are a natural and logical consequence of some of our most promising physical models. The most famous of these is string theory. It proposes that everything in the universe, every particle of matter, every photon of light, even the force of gravity itself is made of tiny, vibrating strings of energy. But here's the catch. For the math to work, these strings can't just vibrate in our 3 dimensions. They need more room to move, more directions to resonate in, like the complex harmonies of a musical instrument requiring a sophisticated design. The number of dimensions in this view isn't arbitrary. It's the very stage on which the universe performs its grand symphony. Interestingly, the idea that reality could have hidden dimensions isn't new. It actually predates modern string theory by decades. Back in 1919, 2 brilliant mathematicians, Theodor Kaluza and Oscar Klein, proposed a bold extension to Einstein's revolutionary theory of general relativity. They made a startling suggestion. What if you added just one extra spatial dimension, a 4th direction of space, curled up so small that we could never see it? When they ran the numbers, something incredible happened. From this single, simple addition, the equations for both gravity and electromagnetism naturally emerged from a single, unified framework. It was a revolutionary insight. It hinted that the existence of hidden dimensions wasn't just some abstract geometric curiosity. They could be the key to explaining the fundamental forces of nature. For decades, however, the idea was considered too exotic, too strange, and completely untestable. It faded into obscurity, a brilliant but forgotten what-if. That is, until the late 20th century, when new mathematical breakthroughs resurrected it, giving it a new life in the form of string theory. In modern string theory, these curled-up dimensions are thought to take on beautiful and incredibly intricate shapes known as CalabiYau manifolds. These are complex 6-dimensional geometries that are theorized to be folded up inside every point of our familiar space, and their shape is everything. The specific geometry of these hidden dimensions determines how the fundamental strings can vibrate. Different shapes correspond to different physical laws. They dictate the types of particles that can exist, their masses, their charges, and the strengths of the forces that govern them. In a very real sense, the geometry of these invisible dimensions might determine everything we observe about our universe. Doors. Why an electron has the charge it does. why gravity is so much weaker than other forces, and why the fundamental constants of nature have the precise values they do. It's as if the blueprint for our entire reality is encoded in the shape of a hidden, higher dimensional space. And yet, despite their deep mathematical importance, these dimensions remain completely invisible. They're too small, their effects too subtle for even our most powerful instruments to detect directly. But their fingerprints might still be written into the fabric of the cosmos. We might be able to find evidence of them in the behavior of gravity at very small scales, in the properties of particles at places like the Large Hadron Collider, or even in the large-scale structure of space-time itself. So, from the fiery birth of space during cosmic inflation to the elegant compactification of extra dimensions, our universe might have started with far more room to move than we can possibly imagine. The universe we see, this vast, sprawling expanse of galaxies and stars, could just be one slice, one three-dimensional sliver of a much larger, higher dimensional reality. But this raises a crucial question. If these extra dimensions truly exist, why can't we sense them? What keeps them hidden from our view? And how on earth do physicists even begin to search for something that might be folded up inside every single atom of existence? To answer that, we have to go even deeper into the strange and mind-bending geometry of branes, strings, and shadows that may define the invisible architecture of our reality. Have you ever wondered what might be hiding in the folds of reality itself? If the early universe birthed secret dimensions, what could possibly live within them? To answer this, physicists have built some of the most ambitious ideas in history mathematical blueprints. For a universe far more complex than it appears, among them, one theory stands out in both its scope and its sheer audacity. String theory. So what is it? Well, according to string theory, every single particle we've ever seen, electrons, quarks, photons, isn't a tiny dot, but a one-dimensional vibrating string. Think of it like a guitar string. Just as a guitar can play different notes, the universe's fundamental strings can vibrate in different ways to create all the building blocks of matter and energy. An electron is one note, a photon is another. But here's the mind-bending part. For the math to work, for these strings to exist and behave as they should, the universe must have extra dimensions. A lot of them. We experience 3 dimensions of space and 1 of time. Standard string theory requires 10 dimensions in total, 9 of space and 1 of time. Later versions, known as M theory, push that number to 11 and introduce something even stranger, branes. In our everyday lives, we think of particles as points. But in M theory, the universe is filled with extended objects of all kinds. You have one-dimensional strings, two-dimensional membranes, three-dimensional volumes, and so on. Scientists call these pi branes, where p is just the number of spatial dimensions they occupy. Now hold on, because this is where it gets really wild. In this view, our entire universe, everything we know, from your phone screen to the most distant galaxy, could itself be a 3-brane. Imagine it as a giant 3-dimensional sheet floating in a much larger, higher dimensional space called the bulk. We are all confined to this brane, stuck on this slice of reality, completely unaware of the other dimensions that exist just outside our perception. But one thing might not be stuck here with us: gravity. Unlike the other fundamental forces, which are tied to our brain, gravity might be able to leak out into the bulk, spreading through those extra dimensions. This could solve one of the biggest puzzles in physics. Why is gravity so incredibly weak compared to other forces? Think about it. A tiny fridge magnet can defy the gravitational pull of the entire Earth. It's as if gravity's true strength is being diluted because it's spreading out into places we can't see. This idea, called the brane world scenario, suggests something profound. While we live our lives in a 3D slice of the cosmos, there could be countless other branes, entire, parallel universes drifting right alongside ours, separated by less than a millimeter in a direction we can't even point to. So if these strings and branes are the actors in this cosmic play, what is the stage? The stage is geometry itself, the intricate shapes of the hidden dimensions. And these shapes aren't random. They have to follow very strict mathematical rules for the laws of physics to make sense. This brings us to something called a CalabiYau manifold. It's a complex 6-dimensional shape that can be folded up so tightly that it becomes invisibly small, hidden within our ordinary space. Each one of these unique shapes acts like the DNA of a universe. Its specific folds and curves determine how strings can vibrate, and therefore what kinds of particles and forces can exist. Some CalabiYau shapes might create a universe like ours, with the right kind of gravity and particles light enough to form atoms. Other shapes might produce universes that are unstable and collapse instantly, or are just totally alien. This leads to a truly staggering idea: the string landscape. If there are many possible shapes, there might be a vast multiverse of possibilities. Perhaps as many as 10 to the power of 500 different universes, each with its own hidden geometry and its own unique laws of physics. Our universe would just be one of many, a universe built not from fantasy, but from the cold, hard logic of mathematics. Let's dive a little deeper into the strings themselves. They come in two main types: open and closed. Open strings have two ends, and they are tied down to our brain. These are the strings that give rise to the particles and forces we interact with every day, like light and electricity. But closed strings are different. They form tiny, continuous loops, and one of their vibration modes corresponds to the graviton, the theoretical particle of gravity. Because closed strings aren't tied down, they are free to travel through the higher dimensional bulk. This is the mechanism that could explain gravity's strange behavior. While all the other forces are stuck on our brain, gravity carried by closed strings can explore the entire multidimensional cosmos. At its core, string theory isn't just about particles, it's a theory of geometry. Every force, every interaction is written in the shape of those hidden dimensions. Scientists believe these shapes were locked into place in the very first moments after the Big Bang, when the universe cooled down enough to settle into one particular configuration. But if these dimensions are real, why can't we see them? Because they would be unimaginably small, around the Planck length, which is about a trillionth of the size of a proton. Detecting something that tiny is far beyond our current technology. Still, their influence might be hiding in plain sight. You might find echoes of them in the strange behavior of dark matter, in ripples in space-time called gravitational waves, or even in tiny variations in the fundamental constants of nature. Physicists have even hoped that high-energy collisions at places like the Large Hadron Collider could create microscopic black holes or other exotic particles that would be a dead giveaway for extra dimensions. So far, we haven't found anything, but the search is far from over. So, let's pull back. Imagine our universe as a vast cosmic tapestry. What we see, the stars, galaxies, and the space between them, is just the visible thread. But underneath it all, there's a hidden weave, a deeper architecture of folded dimensions and vibrating strings. This is the grand vision of string theory and M-theory. Every equation, every calculation, is an attempt to map that invisible terrain. And in doing so, we have created one of the most ambitious and breathtaking pictures of the cosmos ever conceived. A universe where hidden dimensions don't just exist, but define the very nature of everything. We move through the world with effortless confidence in 3 dimensions. We know how to navigate up and down, left and right, forward and backward. But if the universe truly possesses more than 3 dimensions of space, why can't we see them?
Ow.
Why don't we feel them? And why does our experience of reality seem so limited, so flat compared to the possibilities physics predicts? The mystery of the hidden dimensions isn't just about what is missing it. It's about how the universe has concealed them so completely. There are several deep and interlocking reasons why these dimensions might be invisible to us, each rooted in the fundamental structure of physics itself. The first and most straightforward explanation is scale. If extra dimensions exist, they are extraordinarily small compactified, to scales far beyond the reach of our instruments. According to string theory, these dimensions might be curled up to sizes near the Planck length, about 10 to the power of minus 35 meters. To put that in perspective, the Planck length is to an atom what an atom is to an entire galaxy. Even our most powerful particle accelerators can only probe distances down to about 10 to the power of minus 15 meters, still 16 orders of magnitude too large. At such minuscule scales, extra dimensions would be effectively invisible, their effects diluted into the quantum noise of reality. This is the essence of compactification, a process where higher dimensions roll up or fold into themselves during the universe's infancy, leaving behind a seemingly 3-dimensional cosmos. Mathematically, the universe may still possess all 10 or 11 dimensions of M-theory, but 6 or 7 of them are trapped within complex geometrical knots known as CalabiYau manifolds, woven into every single point in space. They are as real as width and height, yet compacted into regions so tiny that even light, the fastest thing in existence, cannot reveal them. So, we daren't perceive these dimensions because they daren't extend far enough to leave a macroscopic imprint. They exist, but only in the fine print of reality. But there's another reason we can sense higher dimensions. We might be stuck inside a three-dimensional brane. In M3's brane world scenario, our entire universe is confined to a three-dimensional membrane embedded in a higher dimensional space called the bulk. Every particle and force we know, electrons, light, magnetisms, a vibration trapped on this brane. We do unmove through the higher dimensions because we are built from the very vibrations that exist only within our 3D slice of reality. It's as if we are two-dimensional beings painted onto a page, living, thinking, and moving, but completely unable to lift ourselves off the paper. This elegant idea is sometimes called the dimensional prison of reality. We are prisoners of geometry, unable to escape the surface on which our universe was written. However, one force might be the exception: gravity. It might be able to travel through the higher dimensional bulk. That's not just poetic speculation. It's an experimentally testable prediction. If gravity can leak into the hidden dimensions, then it should appear slightly weaker in our universe, and that is precisely what we observe. It's the faintest force we know, weaker than electromagnetism by a factor of 10 to the power of 36. Some physicists believe this. Weakness is the signature of gravity's multidimensional existence, strength diluted across the hidden spaces we can perceive. Even if extra dimensions are real and accessible, there's another barrier, one not of physics, but of biology. Our brains evolved to interpret a three-dimensional world because that's what survival demanded. Depth, perception, motion, and orientation are all optimized for 3D navigation, not for the abstract mathematics of higher space. We can't visualize for spatial dimensions any more than a flat, two-dimensional creature could imagine the concept of up or down. Mathematicians can describe these spaces symbolically through algebra, topology, and geometry, but even they admit that our intuition completely collapses beyond the third dimension. We can compute higher spaces, but we can't feel them. Just as the inhabitants of a flat world would perceive only slices of a three-dimensional object passing through their plane, we might only be experiencing projections of higher dimensional phenomena. Things like gravity, quantum entanglement, dark energy could be the faint shadows of interactions occurring in the higher dimensional bulk. In this sense, our failure to perceive extra dimensions isn't a failure of physicside, a limitation of our biological interface with reality. What if we could force them into view? If we could somehow inject enough energy into space, we might be able to unfold the extra dimensions to excite them and make their effects visible. But the required energy would be colossal, far beyond anything we can currently generate. To probe distances on the order of the Planck length, we would need energies near the Planck scale, roughly 10 to the power of 19 giga-electronvolts. That's 1 trillion times greater than what the Large Hadron Collider can achieve. At such energies, space-time itself would behave like a fluid of quantum foam. And the compactified dimensions might briefly open up, allowing strings to vibrate in new and exotic modes. But for now, this is purely theoretical. Our technology and perhaps even the laws of nature themselves may forbid us from ever reaching such energies. That's why these dimensions are sometimes described as being locked behind an energy wall, sealed away since the earliest moments of the Big Bang, far beyond the reach of any human experiment. There's also a more radical idea that our three-dimensional world might not be embedded in higher dimensions, but rather encoded asterisk by asterisk them. This is the holographic principle, a concept born from black hole physics and refined by string theory. It suggests that all the information contained in a volume of space can be represented on its boundary, much like a 3D hologram is encoded on a 2D surface. If this principle is true, then what we perceive as three-dimensional reality could be a projection of data stored in a higher dimensional space. Our universe might literally be a hologram of hidden dimensions, the visible tip of a vast and invisible mathematical structure. This isn't philosophy, it's physics. Calculations in string theory, especially in a framework known as the ADS-CFT correspondence, have demonstrated that certain kinds of higher dimensional gravitational systems can be fully described by lower dimensional quantum field theories. In other words, what happens inside space could be equivalent to what happens on its boundary. If that's true, the hidden dimensions might not be somewhere else at all. It could be woven into the information architecture of the universe itself, always present, yet manifesting as an illusion of 3D space. Finally, there's the greatest cosmic mystery of all, the dark universe. Roughly 95% of the cosmos is made of substances we cannot see or detect directly: dark matter and dark energy. Could these elusive components be the shadow effects of higher dimensions? Some theories suggest that dark matter might consist of particles that move freely through the extra dimensions, interacting only weakly with our brain-bound matter. Dark energy, the mysterious force driving cosmic acceleration, might emerge from the curvature or tension of our three-brain, as it exists in the higher dimensional bulk. In this view, the universe's hidden mass and energy aren't separate mysteries at all, but symptoms of the same geometric truth, that we live in a reality far larger than we can perceive. So why can't we sense the extra dimensions? Because they are too small, too hidden, too entangled in the very laws that define our existence. Because we are atoms, our senses, our very consciousness, are woven into the three-dimensional fabric that conceals them. But invisibility does not mean non-existence. For a century, physics has taught us that reality is far deeper than appearances. We don't see radio waves, yet we use them to communicate. We don't see quantum fields, yet they fill all of space. And perhaps, just beyond our perception, folded within every point in existence, lie the lost dimensions, silent, curled, and waiting to be revealed. For as long as we've looked up at the night sky, humanity has been trapped between wonder and limitation. We've always tried to see beyond the horizon, beyond the stars, and now beyond the very dimensions that define us. But when it comes to visualizing higher space, the hidden architecture of the universe, our minds reach a wall not of ignorance, but of biology. We evolved to survive on a planet, to throw a stone, to build a shelter, to read the curve of a landscape. Our brains are instruments tuned for 3 dimensions. Everything we experience, every line, plane, and angle, fits neatly into that framework. But what happens when nature itself defies it? Our sensory world is a 3D simulation. We see 2-dimensional light patterns projected onto the retina, and our brain reconstructs depth from shadows, parallax, and perspective. It's an elegant trick of evolution, but it's a trick nonetheless. When scientists or artists try to picture a 4th spatial dimension, they're forced to rely on analogy and abstraction. We can't directly perceive higher dimensions, but we can represent their projections, their shadows, in our lower dimensional space. The same way a 3D object casts a 2D shadow, a 4D object would cast a 3D one. And from those shadows, we can only guess at the true form. This shape, known as a tesseract, is the 4-dimensional equivalent of a cube. Its appearance feels wrong. It's seemed to bend. Corners stretch and overlap because our minds can't process for spatial directions at once. We are seeing a projection, like trying to understand a sculpture from its shadow on the floor. Even the best mathematicians admit that higher dimensional visualization isn't about seeing, it's about translating patterns into equations, into relationships we can describe but never truly imagine. Long before string theory or modern cosmology, artists were already grappling with the problem of dimensions. Painters of the Renaissance developed linear perspective, transforming flat canvases into windows of depth. Mathematicians like Piero della Francesca turned geometry into art, using lines and vanishing points to simulate a 3-dimensional world on a 2-dimensional surface. Centuries later, visionaries like M.C. Escher pushed that experiment further. His impossible architectures, recursive stairways, and mirrored worlds reflected a deeper intuition that space itself could bend, repeat, and loop back on itself. Escher didn't know about CalabiYau manifolds or branes, but his art was a meditation on the same question: what lies beyond the limits of perception? Today, artists and scientists continue that tradition, using virtual reality, data visualization, and mathematical rendering to depict higher dimensional structures. In research labs and digital art studios, Simulations of CalabiYau manifolds swirl on screens, their folds and symmetries like living sculptures of hidden space. They are our modern cathedrals of geometry, visual prayers to the unseen dimensions. Well, there's a limit, a boundary where human intuition begins to collapse. In 3 dimensions, our minds can grasp simple geometry. We can rotate objects mentally, imagine their volumes, understand their boundaries. But add just one more dimension, and the logic of space disintegrates. We can no longer tell what's inside or outside, what's near or far. Topologically, everything changes. In 4-dimensional space, 2 objects can pass through one another without ever touching in the 3D sense. A closed surface can exist without an inside. Knots can untie themselves. And distances, so straightforward in our world, become relative in unfamiliar ways. To most of us, this sounds like pure abstraction. But to mathematicians, this is the natural language of higher dimensional geometry. For them, equations and symmetries replace images not because they lack imagination, but because imagination itself is too bound by the architecture of human perception. In 1884, an English schoolmaster named Edwin Abbott wrote a short novel called *Flatland, a romance of many dimensions*. In it, he imagined a 2-dimensional world inhabited by geometric beings, lines, triangles, and squares unaware of any direction but forward, backward, left, or right. When a 3-dimensional sphere visits their world, the Flatlanders cannot comprehend it. They see only a circle that grows and shrinks as the sphere passes through their plane. Abbott's story was meant as social satire, but it became a profound metaphor for our own dimensional limitation. We are, in many ways, the Flatlanders of our own cosmos, confined to a thin membrane of perception, seeing only the shadows of a higher dimensional reality. Physicists often use *Flatland* as a tool to explain how higher dimensions could exist unnoticed. Just as the Flatlanders can't see the height dimension, we might be blind to the additional directions of reality because all our senses and instruments are confined to the 3D brain of existence. There's also a deeper philosophical tension hidden in the question of extra dimensions. When we say something is real, what do we mean? Does real require perception, or just mathematical necessity? For much of human history, what we couldn't see was assumed not to exist until science proved otherwise. Atoms, germs, radio waves, gravitational waves, each was invisible until our instruments revealed their presence. So why not dimensions? In this way, the search for hidden dimensions is also a mirror, reflecting the limits of what we accept as reality. It challenges the idea that perception defines truth. Maybe truth lies deeper in the geometry that underlies all things, even if our eyes can never see it. The philosopher Immanuel Kant once suggested that space and time are not features of the universe, but structures of the human mind, the scaffolding through which we interpret the world. If he was right, then extra dimensions might exist completely outside human intuition. Like colors we can't perceive, or sounds we can't hear, we might live within them, yet never consciously know. And yet humanity never stops trying. Through technology, we are beginning to simulate what we can't experience directly. Physicists use supercomputers to model the properties of higher dimensional spaces, how particles would move, how forces would behave, and how these dimensions could warp our own. Artists use virtual reality to turn those equations into immersive experiences, allowing us to walk through abstract spaces that no living being could otherwise enter. Even in education, virtual 4D models are helping students build an intuition for higher dimensions through motion, interaction, and transformation, bridging the gap between symbolic and sensory understanding. It's a reminder that the human imagination, while limited, is also infinitely adaptable. We may never see extra dimensions with our eyes, but through mathematics, art, and simulation, we can reach toward them, turning the invisible into something we can at least begin to understand. Perhaps the struggle to visualize higher space is not a failure at all, but part of what makes us human. We are beings of 3 dimensions, reaching for something beyond comprehension. Every scientific revolution has begun this way, with a boundary that seemed absolute, until it wasn't. Once we thought the Earth was the center of the cosmos, then that space was static, then that the atom was indivisible. Now we suspect that even the dimensionality of reality, might not be what it seems. To understand the universe fully, we may need to go beyond seeing and learn to think in geometries that defy experience. For now, we are the flatlanders of a higher cosmos, chasing shadows of the infinite, step by step, through science and imagination alike. In our quest to unveil higher dimensions, humanity has built its own temples of discovery, vast machines of steel and magnetism. Buried deep beneath the earth, here at places like CERN, particles are hurled close to the speed of light, smashing together in flashes of subatomic revelation. These collisions aren't just explosions, they are questions hurled into the very fabric of space. How many dimensions does reality truly have? And where are they hiding? The story begins over a century ago, when general relativity had just redefined space and time. In 1919, a German mathematician named Theodor Kaluza made a bold proposal. What if Einstein's equations of gravity could be expanded to 5 dimensions instead of 4? At first, it was a purely mathematical curiosity. But then, something extraordinary happened. When Kaluza extended Einstein's equations, one of the extra terms behaved exactly like Maxwell's equations of electromagnetism. In other words, gravity and light to seemingly unrelated forces could emerge from the same geometric fabric. If space just had one hidden dimension? Later, the Swedish physicist Oscar Klein added a crucial idea. Maybe this extra dimension is real, but curled up so small it's invisible. Imagine a garden hose. From far away, it looks like a one-dimensional line. But get up close, and you see its circular depth. Klein proposed that this 5th dimension might be compacted at subatomic scales, woven into every single point of our reality. And so, the first vision of a multidimensional universe was born, a universe where unseen directions could unify the forces of nature. Einstein himself spent the final decades of his life searching for such a unification, a single mathematical framework that could describe both gravity and the quantum world. But the more he searched, the more elusive it became. His geometry couldn't capture the strange, probabilistic dance of particles revealed by the new physics of the 20th century. It would take another half-century for the dream of unification to return in a radically new form. String theory. In the 1970s and 80s, physicists discovered that if particles were not points, but tiny vibrating strings, the math naturally required extra dimensions. Not just 1, but 6 or 7 beyond our familiar 3 of space and 1 of time. These hidden dimensions weren't optional. They were the essential scaffolding that made the theory consistent, the unseen architecture upon which reality itself could resonate. The vibrations of these strings would determine the properties of particles, their mass, charge, and spin, just like the vibration of a violin string determines its pitch. In the space in which these strings vibrated, these incredibly complex, compact shapes called CalabiYau manifolds would shape the symphony of matter and forces we observe. Each possible geometry corresponded to a different possible universe, a different cosmic melody. Our own reality might be just one verse in an infinite cosmic song. But elegant mathematics alone is not enough. Physics demands proof, something measurable, something testable. So how do you detect a dimension that's too small or too warped to see? At CERN, scientists are searching for clues. If higher dimensions exist, they might subtly alter the behavior of gravity or allow particles to briefly escape into a hidden bulk before returning. The Large Hadron Collider searches for signs like missing energy in particle collisions, microscopic black holes, or unexpected resonances that could be the fingerprints of extra dimensions. So far, no definitive evidence has emerged. But the absence of proof is not proof of absence. Each experiment narrows the possibilities, tightening the mathematical net around what the unseen world could be. Other experiments explore models predicting that gravity might leak into additional dimensions, which could explain why it's so much weaker than the other fundamental forces. If this leakage exists, it might be measurable at microscopic scales, a delicate deviation from Newton's law of gravity, too faint for our ancestors to have ever noticed. And in cosmology, satellites have mapped the afterglow of the Big Bang, searching the ancient light of the cosmic microwave background for hints of dimensional asymmetry, tiny fingerprints of higher dimensional physics frozen at the dawn of time. The next great leap in thinking came from brane theory, an extension of string theory suggesting that entire universes can exist as membranes, or branes, floating within a higher dimensional space called the bulk. In this vision, our entire cosmos, every galaxy, star, and atom, could be a 3D brane embedded in a vast, unseen hyperspace. Other branes might drift parallel to ours, each carrying its own universe, invisible yet right next door. Gravity, being the weakest force, could be the one thing that leaks between these branes, explaining its apparent fragility. And collisions between branes could even trigger cosmic events like the Big Bang itself. Some cosmologists believe our universe was born from such a collision, a shockwave between membranes in the higher dimensional bulk. In this framework, the multiverse isn't a collection of distant bubbles scattered through space, it's a symphony of membranes, all vibrating in unseen dimensions. But how do we see beyond our own brane? If our instruments are bound to 3 dimensions, is higher space forever beyond our reach? Physicists are proposing indirect paths. They look for gravitational waves that might cross from one brane to another, for that missing energy in collider events, or for cosmic rays with unusual signatures. Some even suggest that dark matter, that mysterious substance making up most of the universe's mass, could be a shadow of matter on a neighboring brane exerting gravity, but invisible to our light. The challenge is immense. Every test probes scales smaller than an atom or distances larger than galaxies. The evidence may be buried in noise or hidden in a corner of reality we haven't yet imagined how to look at. But science advances precisely through such uncertainty. Every question, no matter how unreachable, shapes the next generation of instruments, theories, and minds. Perhaps the true revolution won't come from new machines, but from new ways of thinking. When quantum theory and relativity first collided, it required a conceptual leap to accept that time could stretch, that particles could exist in multiple states at once, that reality itself could be probabilistic. Understanding higher dimensions may demand a similar transformation, not just in physics, but in how we perceive the world. To see beyond space, we must learn to think beyond it. Every generation has expanded the horizon of the visible. From Galileo's telescope to the Hubble Space Telescope and beyond, we have consistently turned the invisible into knowledge. And now, as we push against the final boundary, the very structure of reality itself, we are reminded that discovery is not just about finding new worlds, but about finding new perspectives. Hidden dimensions may remain unseen for now, but they shape our theories, our instruments, and our imagination. They remind us that what we call space may only be a shadow of something far greater, a whisper of an unseen geometry holding the entire cosmos together. Every era of science has stood before a horizon, a boundary of understanding that seemed absolute, final. And every single time, that boundary has crumbled. We once thought Earth was the center of everything, and we learned it was just one world among billions. Now, we're facing an even bigger possibility, that the very space we inhabit, the stage for our entire reality, might not be all there is. There may be more directions to go, beyond every horizon we can see. The search for lost dimensions isn't just about physics. It's about what reality itself truly means. The discoveries waiting in this invisible geometry could reshape everything we know, from gravity and dark matter to the very origin and ultimate fate of our universe. The cosmos we can observe, all the stars, planets, and galaxies, accounts for less than 5% of everything out there. The rest is hidden. We call it dark matter and dark energy. They're invisible, but their effects are undeniable, shaping galaxies and pushing the universe apart. Some physicists suspect these dark forces are echoes from higher dimensions, gravitational effects leaking from a hidden bulk into our familiar 3D world. In models known as brane worlds, our universe is a membrane, or brane, floating in a higher dimensional space. While matter is stuck on our brane, gravity isn't. It can spread through these extra dimensions, tugging on our cosmos from directions we can't perceive. What we call dark matter might just be the shadow of matter on a neighboring brane, visible to our light, but felt through its gravity. If this is right, the universe's missing mass isn't missing at all. It's just ... elsewhere. A parallel universe, right next door, pressing against our own, unseen but undeniably real. This idea of higher dimensions naturally leads to another mind-bending concept, the multiverse. But not a chaotic jumble of random worlds, Instead, imagine a structured higher dimensional landscape where each universe occupies its own pocket within a grander cosmic geometry, the language of string theory. There are countless ways for these extra dimensions to fold and curl up on themselves. Each unique shape, each compactification gives rise to a universe with its own distinct laws of physics. This string theory landscape could contain an almost unimaginable number of possible universes, perhaps 10 to the power of 500, each one with its own fundamental constants, its own particles, and maybe its own forms of life. Our universe might not be special after all. There's simply one pattern among countless configurations of the same higher dimensional fabric. If that's the case, then the biggest mystery in physics, why are the laws of nature the way they are? This might not have a single profound answer. This might just be a cosmic accident, a reflection of where our brain happens to be located in that vast multidimensional space, an address encoded in pure geometry. So, are these just fascinating ideas, or can we actually test them? The coming decades might finally give us a glimpse into these unseen realms. The next generation of particle accelerators, successors to the Large Hadron Collider, could probe energies so immense they might just shake the hidden geometry of space-time itself, creating particles that can only exist if extra dimensions are real. At the same time, our increasingly sensitive gravitational wave detectors could pick up faint, telltale ripples echoes from cosmic events, like brane collisions, happening in these higher dimensions. And as we look back to the dawn of time, ultra-precise maps of the cosmic microwave background, the afterglow of the Big Bang could reveal subtle patterns, tiny imprints left behind by the shape of those compact dimensions during the universe's first moments. These aren't fantasies. They're measurable, testable frontiers of science. And every new experiment, every new piece of data, inches us closer to an answer that could forever change what we mean when we say the universe. The challenge of higher dimensions isn't just physical. It's also mental. Our brains evolved to navigate a three-dimensional world. We see in it, we build in it, we dream in it. But the language of mathematics, the foundation of modern physics, tells us that reality isn't limited by what our senses can perceive. To even begin to visualize extra dimensions requires a profound mental leap. It says the same kind of leap that once allowed us to accept that the Earth orbits the Sun, that time can bend and stretch, or that a particle can be in two places at once. Each one of these conceptual breakthroughs expanded not just what we knew about the universe, but what we were capable of understanding as a species. Perhaps as consciousness itself continues to evolve, so too will our ability to grasp geometry beyond geometry, to develop an intuition. For a universe with more directions than we can currently point to, if our universe really does have hidden spatial dimensions, what does that say about the nature of reality itself? Are we living on a lower dimensional surface, like characters in a story? A cosmic shadow play projected by higher, more fundamental truths? Or maybe these hidden dimensions aren't elsewhere at all, but are instead deeply interwoven into the fabric of everything we touch, every atom that makes us who we are. Some philosophers of physics suggest that dimensions are unreally places in the way we think of them. Instead, they are mathematical degrees of freedom. They describe relationships and how things connect to each other. In that sense, the universe's lost dimensions might not be lost at all. It might just be hidden from the particular kind of creatures we happen to be imperceptible to our biological senses. We may be part of a structure so intricate and vast that our three-dimensional world is merely its projection, a simplified version of a deeper, higher-dimensional truth. And understanding that truth would redefine what it even means to exist. Our ancestors once meticulously mapped the Earth, believing they had finally reached the edges of the known world. Then they looked up and discovered the stars. Now, we are mapping the very fabric of space-time, only to find that even this might not be the final frontier. As new experiments, new mathematics, and new generations of brilliant thinkers emerge, we may one day manage to pierce the veil. We might detect a subtle ripple in gravity, discover a fleeting particle, or find a tiny twist in the cosmos that proves the universe truly has more directions than we can imagine. And when that day comes, humanity will have taken its next great step not across an ocean or to another planet, but beyond the very boundaries of space itself. The The search for hidden dimensions is a journey into the invisible architecture of existence. It's a powerful reminder that reality is always deeper, richer, and more mysterious than it appears. It shows us that mystery isn't the absence of knowledge, it's the presence of infinite possibility. We live our lives in 3 dimensions, but the universe may be far more complex layered, folded and infinite in its depth. And someday, when our tools and our minds are finally ready, we may glimpse what lies beyond the visible cosmos and realize that the universe was never small, only our vision was. Thank you so much for joining us on this journey to the edge of reality. If you enjoyed exploring these incredible ideas, don't forget to like, subscribe, and hit that notification bell for more adventures into the cosmos. See you next time.